Hello, math nerds. It's the craziest math nerd of all, Kitty Morgan here, and we're doing part 2 of related rates. So we've got this new thing we're doing, and things are changing with respect to time, and our job is to figure out what equation relates all the stuff that we know and want to find, and once we find that equation, let's implicitly differentiate, plug in everything we know, figure out anything else we need to know, and then let's solve for our problem at hand. So we got a right circular cylinder. There they are. And it says dimensions are changing. All right, well, we got it with respect to time. It has a height of 9 and a radius of 4 at an instant, guys. So this is your instantaneous information. You cannot use this. This is an instantaneous information. You can't use this until after we implicitly differentiate, okay? Very, very important. So we've got to do, we've got to find the change in volume and surface area, and we know some things about it. So we want to find the change in volume and the change in, and I'm weird, I use SA for surface area because it makes sense to what I'm doing, and it helps me kind of put the problem with what everything means. And there's my wind bar. And let's see what I know. The radius is growing at 2 feet per second. So guess what we call that? dr dt, right? Radius is changing with respect to time. And it is growing, so that's a positive. I'm doing that for emphasis, feet per minute. You don't have to put a positive there. Just kind of thinking it through. The height is shrinking, so the h dt is shrinking. What's that going to be? You got it. It's going to be negative 3 feet per minute. Oh no, we have 2 different times. All right, I went and checked on that, and this is a typo on the seconds. That's supposed to be minutes. Sorry about that. And so we want those, and that's something we got to look out for, because if they ever don't match, we got to convert and stuff. So I did check it. That was a typo on that, and that should be minutes. So whew, we avoided a hard one on that one. All right, so we have to write an equation that relates volume to radius and height. So I think the volume of a right circular cylinder does that. So let's see if we can remember how to do that. It's the area of the base times the height. In a right kind of 3D dimensional thing, that's how you do it. So the area of the base is a circle, so it's pi r squared times the height. And if you need that, that will probably be given to you, just to let you know. And then we need to know the surface area of a cylinder. Well, what is that? Oh my goodness. Well, let's see. Yes. So the surface area of the cylinder, we're going to assume that this does not have a top and bottom. So it is just the outside of it. So how do we do that? Well, if you could cut this and lay it out, it would look like this little guy. Would look like that. If you could cut it and lay it out, and what does that look like? Doesn't that look like a rectangle? So this part is the part that we wind up together. So if I could find this is the height of the cylinder. If I could find this length, then I would just multiply them together, and that would give me the area of this. Well, let's roll this back up together then. If you roll it back up together, woo, they draw so much better than I do. Could just use that drawing. Notice that this length that we cut and get it, that length, is really the circumference of the circle. So this really is 2 pi r. I know, right? Because this is the circumference of the circle if we cut it and lay it out. So the surface area is 2 pi r times h. That's so cool. All right, so now if we want to know the change in volume, we would have to find the derivative of this. And the derivative of this is going to be a product. So I'm going to write dv dt, and I'm going to put the pi there, and then I have to do the product rule for this. So first, derivative of the second with respect to time, plus second times the derivative of the first. Now this guy, the derivative of it is 2r, and then the derivative of the inside with respect to time. And all that is multiplied by pi. I'm going to move this little surface area so I can have a little bit more room here. And I'm going to change color so we can see that, there we go. So we can see that surface area. It's 2 pi r. Okay. All right, so now that we've done that, we're going to fill in everything that we know. And now we can put that instantaneous information in there, right? You know what I didn't do? I didn't put that instantaneous information on our wind bar. Crazy me. So the height is 9 feet and the radius is 4 feet. Okay. You know what I'm going to do now? I'm so crazy. I'm going to put it up here because I'm going to run into it. 9 feet and our R is 4 feet. Okay, so now I'm just going to plug everything in. So that yields dv dt is going to equal pi times r squared is 16. dh dt, we have that information, is -3, plus h, which is 9, times 2r, which is 8. dr dt is times 2. All right, so that's -48 and 144. Is that right? -48 and 144. And so I think that gives me 96 right there. So this is 96 pi. Now we got to do our units, right? We know that they're minutes, excuse me, because we had that change. But how are we going to write volume changing? And volume is always going to be your units cubed. Units cubed. So units cubed indicates your volume is changing. Units squared, your area changing. And units is one of your dimensions. Okay? All right. So now let's look at this surface area. Let me change my pen color. So if we want to do the change in this, I'm going to move this up just a little bit so I can see. All right, so we're going to take the derivative of the surface area with respect to time, and that will be, and we do the 2 pi out here, and I still have to do the product rule. First, derivative of the second with respect to time, plus second times the derivative of the first with respect to time, because all of these things are changing as time changes, okay? So everybody is required to use implicit differentiation. And R is 4, and dH dt is 2, H is 9, and dr dt is, wait a minute, I did that backwards, sorry, dH dt is -3. I did not read that correctly. Sorry about that, y'all. And then H is 9, and this is 2. And so, let's see, 12 plus 18 is 6 times 2. And so that's a positive 12 pi. And what we say, this is area changing, right? So it's our units squared over our time. Okay, this isn't bad. And guys, most of the time these kind of things are given to you. You are expected to kind of know some things like the area of a rectangle, area of a triangle, Pythagorean theorem, and things like that. But if it's volume or surface area, many times they'll give you that. Okay? All right, let's do another one. Oh, goodness. Here we go. We got a camera mounted 3,000 feet from the rocket launching pad. And I see that. I'm fixing to label that right now because this distance is not going to change. Okay? And the camera needs to swivel as the rocket is launched to keep it in focus. See, this guy's got to move. See, if this goes up, the camera's got to move. All right. This distance will not change. It's fixed, kind of like the ladder. If the rocket is rising vertically at 800 feet per second, so I'm thinking I probably need to label some things, right? Don't you think? vertical, I normally like to label Y, and horizontal distance, I know that's not going to change, but I'm going to call that X. And I'm going to call this D for distance between the rocket and the camera. And the reason I'm doing that is because it's in the problem and it'll help me make those connections. All right, so it asks how fast is the camera to rocket distance changing? So it wants me to know dt, that's what it wants me to find when the rocket is rising vertically at 800 feet per second. Now, is that a distance? Is that y? I don't think so, because it says feet per second. That's definitely a rate. So I am going to put that as the rate of y changing. So that's when dy dt is equal to, and the rocket is rising, so it's a positive 800 feet per second. It's right on when it is 4,000 feet high, so that is an instantaneous of 4,000. And we want to know dt. All right, so we know x, right? And we know x is always 3,000. So we know x, and we know y, and we know d, and we know this makes a right triangle. And so how do you relate those? The Pythagorean theorem. So I'm going to say x squared plus y squared equals d squared. And let's implicitly differentiate all these. That's 2x dx dt plus 2y dy dt equals 2d dd dt. Okay, so now I need to plug in everything I know. So I've got 2 times 3,000 dx dt. Ooh, where's dx dt? How much is this changing? Oh, it doesn't change, so it's 0. Ooh, we got lucky on that one. All right, now that I've implicitly differentiated, I can put this instantaneous material in there, and that's 4,000. dy dt is 800. I might have to get a calculator out for this one. Hold on a minute. I didn't allow enough room. Excuse me. So 3,000 times 0 plus 2 times 4,000 times 800 equals 2. I don't know what D is. Oh, goodness. Well, you know what? But let's draw that instantaneous triangle like we did last time, right? What's happening at that instant? So I know that this is always 3,000. I do know that. But at the instant, this is our instantaneous triangle. This is 4,000. I don't know if you know much about Pythagorean triplets, but one of the famous ones is a 3, 4, 5 triangle. And so if you have a 3, 4, 5 or a multiple, then like so for example, if I had a 9 and a 12, 3 times 3 is 9, and 3 times 4 is 12, so 3 times 5 would be the hypotenuse. So it's either 3, 4, 5 or a multiple of those. So these are multiplied by 1,000, so this has to be 5,000. Okay? So that's a nice little thing to know, isn't it? 5,000 dt, and that's what I'm trying to find. Okay, so is there anything I have to solve for? Now this is looking good. So that goes to 0, goodness, and then the 2's are going to cancel. And then you have 4,000 times 800 divided by 5,000. Now why did you do that, crazy woman? Because all your zeros are going to cancel on that, right? So you end up with 4 this times 800 will be your dt. And I'm going to grab my hand, go down right there a little bit. 5 will go into that, and we can get an answer pretty quickly. Let's see, that's 16 times 4. Is that 60? Is that 640? I think it is. I think it is, because 5 goes into 816. Well, it's 160. And then that times 4 is 640. What? This is a dimension. So this is feet. I think it's feet. Feet per whatever time per second is d/dt. Okay. When you come back in part 3, we're going to do another, a different take on this problem. We're going to do part B. So please don't miss that. Come on back for some more fun, part 3.